Good morning, everybody. We are going to discuss viral encephalitis today. I hope all of you are keeping safe in the time of corona, keep staying in and taking all precautions for not getting that infection. Now, last time I taught you dengue, and I told you that we had a huge outbreak in our hostel during our second MBBS. These times, you sort of ruminate on the fact that, these infections have been around for a long, long time, and even 30, 40 years back, I remember now in the context of this particular talk today, that I lost a friend to encephalitis during our internship, one of my closest friends. And at that time, we had no idea about what to do, because really speaking, acyclovir, the drug which was launched around 1982 in the market for encephalitis, and this was the year 1984, so it wasn't easily available in India, the drug that acts against HSV encephalitis. There was no vaccine, no good vaccine for Japanese encephalitis. But that is what has changed over all these years, that now acyclovir is the treatment of choice. It's a very safe drug, and so you can deal with an infection which had a mortality of about 70% very effectively and treat it. You also have more than one vaccine for Japanese encephalitis. And there is this vaccine which is most widely used now, the SA-14-14-4 vaccine, which is a live attenuated vaccine which never existed at that time. It was developed by China subsequently and is very widely used and again extremely effective. So Japanese encephalitis itself carries a mortality of about 10 to 40%, and sequelae can persist after that and be quite limiting to people's lives in 40 to 70% of people. And therefore, if we are able to take care of these by a vaccine or by a drug, it sort of puts today's talk in perspective because of these developments that have happened. And therefore, it is worth trying to diagnose these diseases and to see what we can do for them. Nipah virus is another one which is a problem and is a more recent infection starting from 1998. So we have a lot of, and we've seen this huge outbreak in Kerala a couple of years back, I think. So, that sort of highlights the importance of these infections. So what we'll do is, I'll quickly classify for you some of the causes of viral encephalitis, and then after that we will look at some of the more important ones like Japanese encephalitis, herpes simplex encephalitis, and Nipah virus encephalitis. Of course, the most important one, which is rabies, which is still there in South Asia and is again preventable, is a separate topic, so it will be discussed later. So if you look at all the viruses which cause encephalitis, you will see that they belong to different families. The herpes viridae, of course, and you have encephalitis due to herpes simplex virus as a common cause of acute encephalitis. Then you have acute encephalitis due to some of the other viruses like the flaviviruses, and there you have the Japanese encephalitis virus, which is predominant in India, a member of the flaviviridae family. We also have some other flaviviruses in different parts of the world which can cause encephalitis. I won't go into the details of those just now, but you can find them in the books. Then you have some of the Bunya viruses, which are quite common in different parts of the world. We don't see too many of them here, but you have the La Crosse virus, which is very common in the US, and Californian encephalitis. We also have the rabies virus, as I said, rhabdoviridae, which can cause encephalitis. And Nipah, which belongs to the Paramyxoviridae family, is the recent one. So these are some of the common ones, but other than this, you can get encephalitis with some of the enteroviruses which belong to the Picornaviridae family, especially enterovirus 70, 71, Coxsackie A7, which can cause CNS manifestations. And then you also have some other viruses like the Western, Eastern and Venezuelan equine encephalitis, which we don't see in our part of the world. So I think that more or less makes up the list of the common causes of encephalitis. Now moving on to the first one, which is Japanese encephalitis. Japanese encephalitis actually is quite widespread in India. We always knew that there were foci in parts of southern India and eastern India, but slowly it has made a very large focus in eastern Uttar Pradesh around Gorakhpur, which every year sees a lot of cases despite efforts at immunization, etc. And we also now see that it has spread to parts of North India, particularly the parts which have now shifted to paddy cultivation, and in Haryana and in Rajasthan, Haryana, Punjab, you have started seeing cases. So the thing is, what is the link between paddy cultivation and Japanese encephalitis? Japanese encephalitis is spread by the Culex tritineorhynchus mosquito, and this Culex tritineorhynchus is associated with some of the birds which are found around paddy fields. These birds include egrets and pond herons, and you would have seen this rural scene if you have driven through the rural landscape or taken a train through a rural landscape, where you see this paddy field, lovely green paddy fields with a buffalo standing in the middle of it and a bird sitting on the buffalo, which is usually a white bird, and those are the egrets or pond herons. So that is the typical life cycle of this virus, where it circulates between these birds, which are the main reservoir of this virus. The mosquito carries this from the birds to the cattle, and then these cattle are peridomestic, so they will move towards the places where human dwellings are there, and probably at night they'll be there and they are infected by the virus, and that's how human beings will eventually, if those mosquitoes reach the human dwellings, and they'll bite these cattle and then it can get transmitted to humans. So that is the way it works. And if you throw pigs into the mix, pigs become amplifier hosts. So what happens is that these pigs will then start amplifying the virus without actually succumbing to it or getting sick, and they will then transmit it on an even larger scale. So you can imagine this rural scenario where all these things will be thrown together, and that is the classical setting in which the Japanese encephalitis can start. But of course, eventually with urbanization, these mosquitoes will have got access to other settings, and we see much more of it. So this is about the basic epidemiology of Japanese encephalitis and the zoonotic aspect, how the life cycle is zoonotic. The clinical signs and symptoms I'll just describe quickly, because they are common to all forms of acute encephalitis. Basically, it starts with lethargy, malaise, and then the non-specific kind of symptoms, like there'll be fever, there'll be headache, maybe some vomiting, and abdominal pain, nausea. And then you start seeing, because most of the encephalitis in viral encephalitis are actually meningoencephalitis, so you will find some evidence of meningeal involvement, which will be the usual neck stiffness, photophobia, and headache, etc. And then eventually you may start seeing some kind of focal deficits, you may see seizures, you may see convulsions, tremors, ataxia, going on eventually to a sort of confused state, sometimes changes in behavior, and then eventually moving on to stupor and coma, and finally death. And as I said, Japanese encephalitis has a mortality of about 10 to 40%. So these are the usual signs and symptoms, and you must also remember that in about 40 to 70% of people, they are going to have some deficit later on, some kind of behavioral or physical deficit in the long run, neurological sequelae. So how do we diagnose these infections? You can take a CSF sample by lumbar puncture, and using all aseptic precautions. The CSF sample then is paired with a blood sample from which serum can be separated, and you can look at antibodies of the IgM type to the Japanese encephalitis virus in both serum and CSF. You can consider even the presence of these antibodies in the serum as indirect evidence of Japanese encephalitis. So this is usually done by an ELISA test, and a mu capture or an IgM capture ELISA would be the appropriate modality for this. It is possible to grow these arboviruses, and like we discussed in the class on dengue last time, these arboviruses can all be grown in similar ways. You can grow them in mosquito cell lines like C636, and just like dengue, JE is also a flavivirus. So it can be grown in the mosquito Aedes C636 cell line, and it can be also grown in the brains of newborn mice by inoculating it. You can grow it in mosquitoes by intrathoracic inoculation, but the most commonly used one is the C6x36 Aedes albopictus cell line. This cell line, you do not see any cytopathic effect, but what you do see, you can look for the virus by using immunofluorescence with specific antibodies, monoclonal antibodies tagged with immunofluorescent dyes. So that is how we usually diagnose these infections. And then of course you have the polymerase chain reaction, which can be used to detect the presence of the virus in the CSF samples. So these are the various modalities for diagnosis. Now going on to treatment, there is no specific treatment. It will be basically supportive, and I'm not going to go into the details of, it depends on what kind of support the patient needs, whether there is some respiratory involvement, in which case they could need some kind of ventilatory support, etc. Or it could just be, if they have some kind of paralysis, or they could need the usual care for such people, avoiding bed sores, giving them fluids, etc. So if we think about the prevention, there we have we have an option. And as I said, there is this vaccine, which earlier there used to be an inactivated vaccine, which was made in mouse brain, in newborn in mouse brain in newborn mice. Newborn, because as these mice grow, the myelin starts to increase, and then this myelin can be it can lead to an immune response in human beings and more side effects. So this vaccine, the inactivated one, was made in the brains of newborn mice by inoculation, and then harvesting the brains, and then following some procedures for purification and inactivation. This vaccine was made indigenously at the Central Research Institute in Kasauli, and they still make this vaccine, but it has now been more or less replaced, because despite the fact that you make it in newborn mice, there would be some side effects of this vaccine, although it was an effective vaccine. But now it has been replaced by the Chinese vaccine, which is called SA 14144, essentially referring to the kind of passages, etc., that were given to make this virus an attenuated virus. So by multiple passages in various settings, in various cell lines, etc., they have made this attenuated strain. It's a live attenuated vaccine, and this is very effective, and it is used quite widely in the JE endemic regions. The only limitation is that these vaccines have to be given practically every year, because the immunity is not long lived. It lasts for just about a year or so. So that's about Japanese encephalitis. We've talked about the epidemiology, we've talked about the clinical features, the diagnosis, and the prevention. Now I'll move on to the herpes encephalitis, HSV encephalitis. HSV encephalitis is essentially of two types, one that you see in adults and the other that you see in neonates. From a mother who has primary herpes infection, which of course in the Indian setting is not that common, because HSV infection is quite widespread in our population. I would say about at least 60 to 70% of people in our population, or maybe even more, would be carrying the virus. And as you know, these herpes viruses have the ability to remain latent in the body. HSV2 would remain latent in the sacral ganglia, and HSV1 in the trigeminal ganglia. And so HSV1 infection, of course, is far more common. HSV2 being mostly sexually transmitted is less common. So the baby would get it from a mother who's HSV2 positive usually. And this would happen because when the baby is delivering, at that point of time, the mother may have a lesion in the genital tract, which is shedding the virus, and during the course of the delivery, the baby may acquire the infection. So about 30 to 40% of mothers who get primary herpetic genital HSV infection, HSV2 infection, will transmit it to their babies, whereas those who get recurrent infection, meaning that the virus was already there and gets reactivated, it was already there in them sitting in the sacral ganglia, and during pregnancy it gets reactivated and a lesion comes up in the genital tract after reactivation, then the chances of transmission to the baby is about 3 to 4%. Now this type of, this baby, when he's infected, will have generalized herpetic infection, which could involve the mucous membranes, it could involve the skin, it could involve other organs, and also the CNS. So if this type of encephalitis, neonatal encephalitis due to HSV, would be a more generalized encephalitis. It would not be a focal encephalitis, it would be diffuse encephalitis, affecting different parts of the brain. And there is a role in managing this for the HSV antisera, immunoglobulins, and along with the drug, which is acyclovir. I'll come to more details about the drug a little later. So this is about the neonatal herpes simplex encephalitis. The adult herpes simplex encephalitis can occur again due to primary herpetic infection, which again, because adults, 60 to 70% of them may already have the infection, so they may not, they may usually, the infection would be a reactivation in these people. And a reactivation can also lead to encephalitis, because the virus gets reactivated and can travel up by retrograde axonal flow right up to the central nervous system and then cause herpetic encephalitis. So this HSV encephalitis in adults is different in terms of the involvement of the brain. It primarily involves the temporal lobe, and you will see some typical EEG changes in the EEG, and because of, if you see temporal involvement, that in an acute encephalitis case, it casts a strong suspicion on herpes simplex virus. So the clinical signs and symptoms we've already discussed, they are the same as for JE or for any of the other acute encephalitis types. Going on to the diagnosis, the gold standard for diagnosis of herpes simplex encephalitis is PCR, polymerase chain reaction, or real-time polymerase chain reaction. The probability of isolating it from CSF is low, but it can be grown in the Vero cell line, Burwet monkey kidney cell line, and will produce a cytopathic effect. HSV2 usually leads to syncytium formation and sometimes even giant cell formation, but HSV1 usually manifests with ballooning. So you can actually see the cytopathic effect and you can detect this virus in cell lines, but as I said, the chances of picking it up on cell culture are very low, and therefore the gold standard remains the polymerase chain reaction for the HSV DNA. As far as the antibody tests go, serological tests go, all they can tell you is whether this person has had herpes simplex infection in the past or in the near future. Usually very hard to differentiate between acute infection and reactivation because if IG, in the reactivations you'll find some increase in the IgG perhaps, but the IgG could be there from before in these people. It's a little difficult to diagnose, but what you can find out is that there are, if you look at the glycoprotein G of the herpes simplex virus, that differs between HSV1 and HSV2. So if you look for antibodies to the glycoprotein G of HSV2, that is considered somewhat specific of herpes simplex virus 2 infection in this person, in the mother. But in case of neonatal herpes, or in which is where the differentiation into HSV1 and 2 antibody responses is important. But other than that, serology doesn't really play a great role in the diagnosis of herpes simplex encephalitis, which rests primarily on PCR, as I said. As far as the treatment goes, that is where we have an excellent drug, which is acycloguanosine, or more commonly known as acyclovir. Before this drug became available, the only way to diagnose herpes simplex encephalitis was to do a brain biopsy, and that was, as you can imagine, it was a very invasive procedure, because the antiviral drugs at that time were more wide spectrum drugs which had a lot of side effects like interferons and so on, and you would not want to give these drugs without being 100% sure of the diagnosis. So what acyclovir changed was that you no longer needed brain biopsies because it is an extremely safe drug. And why is it a safe drug? There are many reasons for this. At many levels it is specific for the virus. The first thing is acyclovir is actually a prodrug. The acycloguanosine is a prodrug. It has to get phosphorylated to become the active form. So the first phosphorylation, that is from acyclovir to acyclovir monophosphate or acycloguanosine monophosphate, happens more efficiently in cells which are infected with the herpes virus because it uses the herpes virus thymidine kinase more efficiently than the cellular kinases. So only those cells in which there is viral herpetic thymidine kinase present are able to convert the drug from its prodrug to the monophosphate derivative, and the efficiency is at least a few hundred times higher for this than for cellular kinases. So the likelihood that the drug will turn into the monophosphate is much more in a herpes virus infected cell. The second thing is that this drug will be more effective on herpetic DNA polymerase than on cellular DNA polymerase. So with these two checks, the drug is able to act much more efficiently on the herpes virus infected cells than on the uninfected cells, and therefore there are less side effects. It's an extremely effective drug, and it can be given intravenously in cases of herpes simplex encephalitis, and can treat this infection, which otherwise would have had a mortality of 70%. So this was about the pathogenesis of herpes simplex encephalitis, the clinical features, the diagnosis, and the treatment. There is no vaccine as of now. Finally, we move on to the third virus, which is the Nipah virus. The Nipah virus is a more recent entrant to the spectrum of viruses which can cause encephalitis. In 1998, and it's actually a paramyxovirus. It belongs to the family Paramyxoviridae, in which you have many other viruses like the measles virus, the respiratory syncytial virus, and so on. There are lots of important human viruses there. It belongs to the genus Henipa virus, and these Henipa viruses basically comprise of the Hendra virus and the Nipah virus. The Hendra virus actually was seen in horses and the people who were caring for them for the first time in Australia, and has caused very limited human infections. But the related virus, the Nipah virus, and the Hendra was sort of described first in 1994, whereas Nipah was first described in 1998 from Malaysia in a community from which the name is derived. These people were basically pig farmers, and they developed encephalitis, and later on it was identified that this virus, they tried to look for the source of the virus, and this outbreak of encephalitis, they sort of localized it to the pigs, and there was culling of pigs, etc., and it was controlled. After that, another strain of this virus emerged in Bangladesh, which was different. Pigs were not involved there. The transmission was directly to humans, not through any of the known animal reservoirs at that point of time. And later on, it was worked out that this virus was actually transmitted by fruit-eating bats, and it was excreted in the infected bats in their urine and in their other secretions and excretions. And those of you who are familiar with or are Bengalis would know that you have this palm gur, which is consumed there, and even in liquid form, etc. And there were studies, and so in Bangladesh also they have a similar practice. They climb up these palm trees and they make a hole in the stem of the tree, and then they take out the juice from those stems, and from that they make gur, or they make a liquid which is also used in sweets, etc., particularly in the winter season. So this was actually what happens is that they leave these little buckets hung up on those trees after climbing up and making a hole in the stem, and the sap keeps dripping into these containers, and then they leave it there, and then pick it up maybe the next day or after it gets filled up. But what happens is at night, and there are beautiful videos of this, the bats come in, and these bats are roosting higher up on the trees, and they come down and they come and they actually drink that sap because they are fruit-eating bats. So if you give them a good supply of sap, of nice sweet sap, they can't resist it, and they come there at night and they drink it, and in the process, if they are infected, they pass on the virus through their secretions and excretions into this sap, and then that can indirectly infect human beings. So that is how this interesting cycle was worked out. Of course, after you convert it into good, etc., there are a lot of steps that it goes through, so it's unlikely that it's going to be infective, but in the liquid form, there is always a chance. So Bangladesh had this outbreak in 1994, and after that, 1998, and after that, there have been regular outbreaks in Bangladesh and just across the border in West Bengal. So we have been seeing this throughout until the recent outbreak in Kerala, where again these fruit-eating bats were implicated. And these fruit-eating bats have a very large footprint across a lot of much of Southeast Asia, South Asia, etc. Very large footprint going. So you can see some of the maps in the books, which show you how far these pteropus bats, Pteropus, the pteropus fruit-eating bats have this flight range, which and distribution across a large part of this, large area in this part of the world. Now, how does it manifest? What happens is that once people are infected, so this is also zoonotic disease spread through bats. A lot of zoonotic disease now have been associated with bats. The Ebola virus has been associated with bats. The initial SARS virus was associated with bats. This one, there is some link, but not very clear cut. So these fruit-eating bats seem to be playing a large role in zoonotic diseases. They have been around for possibly from much before human beings, and they have these dwelling places in caves or on top of trees and so on. So they have been they have been carrying or harboring many of these viruses without getting sick themselves, etc. Anyway, so this virus, when a person gets infected, the incubation period can go up to about 14 days for this, from about 4 to 14 days, and the person would again present with the typical symptoms of acute encephalitis, which I have earlier described. But in addition to that, there is also respiratory involvement. And as you know, this is a paramyxovirus, and that is the same family, which is the family of measles and respiratory syncytial virus, all of which are transmitted through the respiratory route. So it is through the respiratory route that you expect that this infection is transmitted to. Through aerosol, etc., and even from those secretions which are there in the palm sap, etc. It is essentially by aerosolization. So what happens is that you will see a lot of influenza-like illness initially, and then it may go on to more severe respiratory disease, including ARDS, including sometimes consolidation, etc. And this will accompany the encephalitis. So you'll have a picture of respiratory as well as CNS involvement. In addition to that, a large percentage of cases also have shown thrombocytopenia, and there is an element of vasculitis also there, which can ultimately lead to multi-organ failure. And this, it becomes a complex picture. It's not just an acute encephalitis on its own. So this is how Nipah presents, and as of now, there is no specific treatment for it, and there is no good vaccine for it, and it just occurs as these regular outbreaks in different parts of the country. India, of course, has in different parts of the world, but right now focused on Bangladesh and West Bengal, where they have regular outbreaks, and the first time we had it in Kerala recently. So these are the common ones which I wanted to discuss today. Other than this, of course, as I said, rabies is extremely important, and there's an excellent post-exposure vaccine which we are all aware of after dog bites, etc., which one can use to protect oneself, and I think there's a full class on rabies which will happen. So to summarize, these acute encephalitis acute encephalitis is caused by a number of viruses, which include the rabies virus, the Japanese encephalitis virus, HSV, and Nipah virus. There are many others which I mentioned earlier, including the enteroviruses, the other, Bunya virus, some of the Bunya viruses, which we don't see that commonly in India, some of the other flaviviruses, etc. So these infections are either mosquito-borne or zoonotic much of the time. They have a zoonotic link. There's a treatment available for herpes simplex encephalitis, and there's a very good vaccine for Japanese encephalitis, and also, of course, for rabies. Other than this, there are some other encephalopathies, etc., which have been linked with viruses, which I'm not going into, but you should know at least a little bit about them before we close. Like there are post-infectious encephalitis also, encephalopathy seen after many of the exanthems, like measles, rubella, and other infections like influenza, etc. So you can see post-infectious encephalomyelitis kind of scenarios, which have an immune component to it. You can also see other late sequelae like subacute sclerosing panencephalitis, which can happen many years after an acute measles episode, and it usually presents with learning disabilities, a sort of decrease in school performance, etc. in school-going children. But now the spectrum in the West, because of better immunization in the early age, and it has shifted a little to older age groups, say towards 25 to 30 years instead of the usual, which was about 10 to 20 years. So that is so those are some of the unusual ones, but we still see them because we don't have our measles immunization. There are still some gaps, I guess. So we still see cases of subacute sclerosing panencephalitis. So some of these other types, and then there's of course the PML, or progressive multifocal leukoencephalopathy, due to the JC virus, which is so there are some other rarer ones which I have not gone into, and I think you do not possibly need to know too much about them. So with this, I would like to thank you for listening patiently. If you have any questions, you can put it up you can type them out and I can try and answer them. So if there are no questions, thank you so much for being online, and keep safe. We have a few more days of the lockdown, then let us see how things go. And I guess virology always finds a way to remain relevant, and I hope we will be through this crisis soon and be face to face with each other at some point of time in the near future. Thank you so much.